the ions, and I quickly realized that, if you guys don't use, if you don't use a different color font on your answers, it makes grading on the computer really hard. With a piece of paper, it's easy because you're all using like pencils and pens. It's easy to see what you're writing. So after grading about a half a dozen, I decided I'm just going to give you all the answers. And so here we go.
Oh, wait.
Oh. Well, I'm waiting for you. Okay, so remember that the atomic number makes a pretty good proxy for the number of electrons. Greg, you have a question?
Yeah. So this for grade stuff?
Yeah. I mean, just normal, the usual formative assignment, yeah. So usually, if an atom is neutral, the atomic number makes a pretty good proxy for the number of electrons. That is not the case with an ion. So for instance, lithium +1, while its atomic number is 3, it has 2 electrons. And those 2 electrons are going to fill the 1s orbital up down. Okay, so that's your answer for that one. And then no noble gas configuration is too small. Now titanium we've done in class. Titanium ends 4s2 3d2. So it's noble gas is argon 4s2 3d2. Oxygen 2- we did in class. So oxygen normally has 8 electrons. The 2- tells us it now has 10. So we fill up not only the 2p4, but the 5 and the 6. And its configuration is 1s2, 2s2, 2p6. Now the difference between titanium and titanium 2+ is the 2+ tells us 2 electrons were removed, and the 2 electrons that get removed are the 4s2 electrons. So there's the 4s2 in titanium, and the 4s2 are missing in titanium 2+. So titanium 2+'s noble gas configuration is argon 3d2. Okay. The same thing happens in zinc. Zinc 2+, those 2 electrons that are removed are the 4s2 electrons. So the 4s2 is missing from zinc 2+'s noble gas configuration. We did chlorine in class. So chlorine would normally end 3p5, but the -1 tells us it gained an extra electron. So it has 18 electrons, and that takes to 3p6. So chlorine's noble gas configuration is neon 3s2 3p6. Iron, this normal iron, normal old iron has the 4s2 3d6. The 4s2 is in there. So iron's configuration is argon 4s2 3d6. Calcium 2+ we did in class. So calcium 2+ is missing its 4s2. The last 2 electrons in calcium are the 4s2. The 2+ tells us the 2 electrons were removed, and it's the 4s2 that were removed. So it has the configuration of argon, so we can't just write argon. Okay? When we're doing calcium 2+, we can't just write argon, we have to write neon 3s2 3p6. Silicon ends 3p2, so we have the 3p2, this normal old silicon, 3p2, and that's its configuration. Nickel, no change to nickel, it's just normal nickel. 28 electrons from atomic number 28, 4s2 3d8. Arsenic is atomic number 33, has 33 electrons, and it ends with 4s2 3d10 4p3. So there's arsenic, right? Oh my gosh, right there. I didn't even catch that mistake, so I'll fix that later. I'll fix it later. And then bromine, down to, it's in the periodic table. I made a mistake in one of them that needed to be fixed by a student. So bromine -1, bromine would normally have 35 electrons. Now it has 36 because of the -1 charge. Remember, electrons are negative. You get another electron, it's a negative charge. And bromine's configuration becomes argon 4s2 3d10 4p6. You can't just say krypton. Okay? It is isoelectronic with krypton, but you can't just say krypton. That's against the rules. So you got to show argon 4s2 3d10 4p6. And then antimony 3+, antimony's hanging out in the middle of the periodic table, and 3+ means it's going to lose 3 electrons, and it is the p3 that it's going to lose. So it's going to lose its p3, and it's going to end krypton 5s2 4d10. And then finally, tin, right next to antimony, did not lose its p electrons, it ends p2. Okay. And then once again, the idea is isoelectronic are 2 or more things that have the same configuration. Calcium 2 plus and chlorine minus are isoelectronic with argon. Okay, so calcium 2 plus and calcium and chlorine minus are isoelectronic with each other and with argon.
Can you take it back a couple steps and slow down? I'm sorry.
What do you want? Yeah, I can. So which one do you want to talk about?
Can we start back at titanium plus or losing 2 electrons? So
Sure.
there.
Okay, so titanium is found at the 3D2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. That's titanium's electron configuration. Okay, which means titanium has a noble gas configuration 4s2, 3d2. Okay, now in turning titanium into an ion, you're going to remove 2 electrons. And the 2 electrons that are going to be removed are going to be the 4s2 electrons. So titanium without an ion is going to have all 22 electrons. Titanium as an ion will lose 2 electrons. That's the +2. Remember, electrons are negative.
So why does the positive 2 titanium end in 3d2 and not 4s?
Because the 4s2, if the options are removing a 4s or removing a 3d, the 4s gets removed first. So they don't unfill. They don't refill in reverse. They don't get removed in unfilling order. The 4s always gets removed first.
For the first titanium up there, why is there 4 electrons in the 1s2? Or is that on all of them?
No, you're looking at the answer from above it. So
Well, because
One
right
is
there.
2, 2s2, 2p6. This is the answer from above it. This is lithium's answer.
Oh.
So
it is.
1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4p6 or 4s2.
Doesn't zinc have an atomic number of 30?
It does. Did I have a mistake in here?
Yes, you do.
Yes.
Okay. So yes, that should be 30. Thank you. I know it's hard when your heroes fall, but we are human. We do make mistakes.
Are you fine?
So I will fix that. Any other questions about this stuff before we move on to the last thing you need to know about electrons? All right, cool. So there's that. And you can watch the video and listen to it and all that stuff later. Boop. It's always on the YouTubes. See? There's the YouTubes. See? Stream. Okay. Anyway, okay. So the last thing you need to know about electrons is there's this idea of valence electrons. Valence electrons are the highest most, the electrons in the highest most shell. And they are the sum of the highest s and p orbital. Okay? So for instance, lithium has a 2s1 electron and beryllium has a 2s2 electron. Since that's the highest shell and there is no p, lithium has 1 valence electron, beryllium has 2 valence electrons. Now boron has a 2p1 in addition to the 2s2, so boron has 3 valence electrons. Carbon has 2p2 in addition to 2s2, carbon has 4 valence electrons. And the pattern continues. Because remember, the thing to remember about a valence electrons, it is the sum of the s and the p in the highest level. So you just go across and you say, I got 1, 2, 3, 4, 5, 6, 7. 1, 2 for the s, 3, 4, 5, 6, 7, 8 for the s and the p together. Yes?
So like argon and neon have the same amount of valence electrons.
Yes, and they would have 8. They would have 2 from the s's and 6 from the p's. Yeah, and that's the pattern that comes up. When you look at a group, it doesn't matter where you are, how deep you are in the group, that group is going to have the same number of valence electrons. Now, it's important to remember that 4s2 is right here and 3d10 is right here. The d always gets pushed one level down. So if we can ignore the d when we're counting the number of valence electrons. Everything in group 1 will have 1 valence electron. Everything in group 2 will have 2 valence electrons. Everything in group 13 is going to have how many? 3.
What? That's messed up.
So
I
then,
didn't come up with the system. It's
so
1, 2, 13, 14, because we can ignore the D. This is groups
Oh.
3 through 12.
We should ignore that.
Yes.
Oh.
Because the D block, we don't ignore it just because the D block is lower in energy. So in period 4, you have the 4s and the 3d and the 4p. When we're looking at the valence electrons, we only care about the electrons in the highest shell. So everything in group 1 has 1, everything in group 2 has 2, everything in group 13 has 3, everything in group 14 has 4, group 15 has, group 16 has, group 17 has, and group 16 has 6. And group 18 has 8. Okay? So you just add the S's to the P, 1, 2, 3, 4, 5, 6, 7, 8. Question?
So how would you calculate like the Z?
Oh, zinc's valence electrons?
Yeah.
This is one area we are going to just ignore them just because.
Okay.
Because when you're looking at a D block electron, they are called multivalent. And I will tell you why that is next unit. Yeah, so we're going to ignore, for the next 2 units, we're going to ignore everything that isn't an S and a P block. We're going to ignore the D block and the F block, and we'll learn about why they are called multivalent and why they are special later on. There's a reason that your electronics are made out of copper and not selenium. It's because of that. Other questions before we move on? Okay, so this idea of an octet is, how many electrons are an octet? 8. The noble gases have an octet. Okay, when you look at the highest S and P, S2, P6, that's an octet. Argon, S2, P6, that's an octet. And it continues on. All atoms, I told you yesterday, all atoms want to look like noble gases. Well, more accurately, all atoms want to have octets. They want to have a filled outer shell. Okay? And they get that by gaining or losing electrons. So if you're chlorine, there's chlorine, we talked about this yesterday. Chlorine is in group 17, which means it has how many valence electrons? 7. If you have 7 valence electrons and you want 8, what are you going to do?
gain an electron.
You're going to try your best to gain an electron. Fluorine will do that too. Fluorine's also got 7. It's going to try its best to gain 1 more electron. Because if you have 7, but you want 8, you're going to try really hard to gain 1 electron. Kind of like if you're collecting Pokemon cards and you've got almost the entire set except for 1 Charizard, you're going to try really hard to get that 1 Charizard. So fluorine, that 1 electron is the Charizard. Yeah.
So is it always gonna try to fill like up, like with say like sodium try to become argon, or try to become
Excellent question. Like almost perfect. So yes, the question is does it always go up, or will sodium try to gain 7 to become argon, or lose 1 to become neon? What do you think is easier for sodium to do? Lose 1 and look like neon, or gain 7 and look like argon? And it is. So sodium, it's easier for sodium to lose 1 and look like neon than it is to gain 7 and look like argon. And that's the pattern. If you have 1 valence electron, it is easier for you to lose 1 valence electron than to gain 7. If you have 2 valence electrons, it's easier for you to lose 2 than gain 5.
So what about silicon?
Okay, so let's go ahead and look at the pattern. Group 1 has how many valence electrons? 1. Group 2 has how many? 2. Group 13 has?
3,
Group 14 has?
4,
Group 15 has?
5,
Group 16 has?
6,
Group 17 has?
7,
Group 18 has?
8,
All right, so if you're in group 17, you want to gain 1 electron. If you're in group 16, you want to gain 2 electrons. If you're in group 15, you want to gain 3 electrons. If you're in group 1, you want to lose 1 electron. If you're in group 2, you want to lose 2 electrons. And if you're in group 13, you want to lose 3. And part of the reason we're all made up of a whole bunch of carbon is because carbon's group has 4 valence electrons. It is equally easy for carbon's group to gain 4 and go up, or lose 4 and go down. Okay? So what makes carbon so unique and so useful is it is equally easy for carbon to gain 4 or lose 4. Does that idea make sense?
Yes.
Yeah.
Okay, any other questions? John?
How come does the D block have like a group?
No, we're gonna ignore the D block because they are what's called multivalent, meaning their valence electrons are all over the map. There's no rule for them that you know of. So you can learn that rule in the future, but right now we're just gonna focus on this unit and the next, we're gonna focus on the S block and the P block. All right, questions? All right, so that is everything you need for electrons. So for the rest of class, what I'd like you to do is finish worksheets 1 through 3, and then this is the unit test review. If you are current on 1 through 3, you can work on this. It's a little bit of everything that you're gonna see on next week's test. So you got some electron configurations, orbital diagram, noble gas configurations. You got some questions about orbitals and orbital types. Then you got some questions about electromagnetism and some calculations of electromagnetism. And then some ion configuration. A little bit of everything you'll see on the test. So go ahead and work on that.
What day is the test on?
Wednesday.
Wednesday. The solar lab is gonna be Monday and Tuesday, and then the test is gonna be